Alright, so hello and welcome. Good evening. Wanted to quickly return to a problem I was working on previously. I'm going to just take a moment to see if this has started. Looks like it did. Okay, great. So, howdy. I was working on this problem, this elimination game problem, and earlier today, and I've been kind of pondering it as I go about the rest of my day, and or went about the rest of my day. The day's kind of over now. And I realized something kind of funny about this algorithm. So let's jump into it quickly. Something kind of fishy going on here, and that is the following. Right, so I'm not going to read the question again. Well, I could. Okay, a list of integers, 1 to n, sorted strictly increasing. Apply the algorithm left to right, remove the first number and every other number, and then right to left, remove the rightmost number and every other number, and then repeat this over and over until there's only one number left, and then return the last number that remains in the array. So to give an example, if you have n is 9, 1 through 9, remove 1, 3, 5, 7, 9, all the odd numbers, and then every other even number from the right, or every other number from the right, and then the first number from the left, there's no other number to remove, and then left with 6, and bada bing bada boom, you've got your algorithm, right? So this is a super interesting question. Now what I noticed about this question is that it's related to, I had some notes, but I'm not going to show you that yet. Had some notes, I'm actually going to delete this. Had some notes, and I deleted them because I didn't want to keep them. I didn't think it was really, didn't really need to keep notes for this. But this is a really interesting question, and I kind of teased out sort of an algorithm. After some kind of thinking about it, it looks like there's an approach where you could basically say, okay, let's only try to keep track of the first 2 elements of each sequence, and basically you're going to have a choice between either the first element or the second element, and you can actually, there's a way you could generate the next expected element, and you can kind of see that because you remove, as it turns out, you're removing half of the elements at each step, roughly half. The step between each next element is a power of 2. So here it's 2 raised to the 0, here it's 2 raised to the first, right? 2, the difference is 4, and here you have 1 element left. But the difference here would be 8, right? The next element in this sequence would be 14. And it kind of just so happens to work out that way. Now you could probably prove that that step works that way, that you would sort of always have that, and I kind of had the beginnings of that. I didn't really prove it, but you can kind of see it, that you can kind of prove at each step there's a kind of a difference that's a power of 2. Now what's super interesting about that is that I was able to say, okay, well then the logic seems to come out where at every step from left to right, you're always going to choose the second element, right? You're always going to eliminate that first element, no matter what. But every other step, since you're removing elements right to left, it matters whether or not you're dealing with an even or odd number of numbers left over in your sequence, and that'll determine whether or not you pick you keep the first element or the second element, right? Which one you remove, and that's very significant, right? So that allows us to actually make a really efficient algorithm, in terms of the number of bits, right? Because each time you basically bit shift the number of elements, is just divide by 2 at each step. So we have that happening, right? Bit shift by 1, divide by 2, and then we have this difference between the elements is increasing at each step. Bit shift to the left 1, right? Multiply by 2, right? Because these are powers of 2, and finally we have this toggle that keeps track of, well, we only really make a decision based on odd or even of which element, the first or the second element to keep or to remove. We only make that decision every other execution, I guess, or every other step of the algorithm, we'll say. What's super interesting about this is, because this is if you AND with 1, when t has a particular value in that spot, that's when we add that power of 2. What's interesting is this actually could be basically you could wrap this algorithm up, or you could understand this algorithm in a different way, in that it could actually be bits that you have in another integer. And because of the toggle, the only bits you would care about are every other bit. So a number, an integer that would look something like this, where it would be sort of like, it would be 0, 0, 1, 0, 1, 0, 1, and so on. If you were to AND this original n with that integer, then you would actually end up with something very similar to this, right? Because the this difference is increasing. The step is increasing as you progress from right to left on each bit, right? As this bit, so this is a power of 2, as are the values of bits, and the toggle gets skipped every other value, right? Every 0 you wouldn't bother, you wouldn't do anything. And finally, you only would add if there's a 1 in this t, which is just n, and basically being processed right to left. So my hypothesis here is that you can actually rewrite this as n and a particular number. And this particular number was what I was doing before. This number is going to be 0, 1, 0, 1, dot, 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 all the way to the end, right? For 32 bits. It's unsigned 31 bits. So this number would be 2 raised to the 30th, excuse me, it would be 2 raised to the 1st plus 2 cubed plus 2 to the 5th, so on, up to 2 to the 29th, actually is what you would want. This is what we're after. So let that be x. And we're going to say 2 to the 30th, 2 to the 29th, etc., down to 2 to the 2nd, 2 to the 1st, to the 0. That's going to be y, where y is the, this is the largest, this is a full binary expression, right? This would just be 1, 1, 1, 1, 1, 1, dot, 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 1, 1, 1, right? Okay. And what's interesting about this is you can have there's actually you can calculate y, x from y, right? You could say take 2 times x, and that's going to be 2 to the 30th plus 2 to the, it would be 28th, right? The 27th, 28th, dot, 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 2 to the 4th plus 2 squared. And this is very close to y, right? If you take y minus x, that is almost the same thing. It's 2 to the 30th plus 2 to the 28th, right? We subtracted 29, subtracted 29, 27, etc. Except the thing that we're missing, y minus x, is plus, we removed 2 to the 1st, so we have 2 to the 0, and we have 2 squared. So we have 2 squared plus 2 to the 0, which that's just 1, right? So y minus x is almost the same thing as 2x, except for this 1 value here at the end. If you were to add 1 to this guy, it would be the same as this guy, which means that y minus x is equal to 2x plus 1, which means that y is 3x plus 1, which means that x is y minus 1 over 3. Oh, interesting. Well, I just happen to have calculated that already, right? So that number, that int max number, is 2 raised to the 31st minus 1, right? That's y. So now if you subtract 1, first off, that's divisible by 3, which is pretty interesting, which is what we just learned. And this seems to be what x is. And so you can just take an integer of this number and AND it with n, and in theory, that should give you the same result. Huh. Is that so? Wrong answer. That's disappointing. I thought about this for so long too. You gotta be kidding me, really? Oh, really? No. So close. Hold on, let's try some other numbers. How far away are we? We can't be that far away. We've got to be very close here. I don't know. That's pretty far away. Huh. Well, maybe I'm wrong then. I don't know. Thought I was right. Really? You're kidding. How? Really? Wow. No kidding. Let me test something. I don't think my math is wrong in this one. What does this do? I think that needs to be. I think I have to note is that I am often wrong. All right, so yeah, 0, 1, 0, 1. Yeah, I was right. Okay, 0, 1, 0, 1, 0, 1 all the way down. That's what we're expecting. Oh, and probably should remove these test cases. These are just random test cases. It shouldn't matter. We could just generate those. No problem later. Okay, 0, 1, 0, 1. Okay. That's actually what I was expecting. Huh. T toggle. It's true initially. Oh, excuse me. That actually means you always add when toggle is true. Oh, whoops. And then you're only checking. Oh, interesting. And then you're not adding. Oh, maybe this should be different then. Okay, I got it wrong. So you're always going to add. So actually, the ones should be on the other side. The ones should be. It's more like this one, 1, 0, 1, 0, right? Where there's always a 1, and I actually think it's an OR you should do. So interestingly enough, you can just subtract and use OR. Oh, okay. Right. If you add this to, hold on. Let's see what happens when we do this. Take this number, try that one. What happens when we do this? The calculation for these numbers, I think, is the same. But I think it's the other way around. I think I misunderstood something. Output. Oh. Wait. Hold on. What? Oh no. No. If you have a 0 for n. Oh, I see. Interesting. That's awkward. Right, OR doesn't work now. Man, there's people that smoke pot. I can smell it. It's obnoxious. Trying to have my window open to get fresh air instead of getting freaking hot. And the building's a non-smoking building, so it's really annoying. Anyway. So what was I doing? So oh, well, actually, we don't want to add. We don't actually want to do it this way. We want to. That's a good question. I'm thinking about it. How do we? Uh-oh. We do want to do an XOR, or do we want to do an? We want to do an OR, but we don't want to do. Basically, we want to clear the ones out of this that are too far to the left. Uh-oh. Now, how do we do that? Well, that's interesting. Well, we could do this first. No, it doesn't work. Oh, never mind. Oh, I think I know what to do. Okay, all right. I'm some bit manipulation we got to do. So if we bit flip and if we do this, what about this? Do these things. All right, if we do this, and the parts of n, so this is going to take everything that is basically all of the zeros to the left of n are going to become ones. No, that doesn't really help us. I don't know, man. Shoot. How do we do this? I don't know. Like I know what I want to do, but it's not. Basically, we want to clear the left half of this integer. Everything to the left of the most significant bit of n we want to clear, and then we want to use an OR. There is a way to do this. The problem with finding the most significant bit is that it actually takes like a loop to run. It's kind of annoying. And if the whole point of this is to like, be clever and do like one operation or something, or a few operations, bit operations, then we kind of defeat the purpose a little bit here. Oh man, this is gonna take longer than I thought. I thought this was gonna be really quick. How do we do this? Huh. What if you flip the bits for n? What happens if you do this? N XOR this guy. What does that give you? And then you flip that again, and then try to OR this. This is real funky, but I don't know. I don't know. What does this give you? This is real funky. No. Okay. Thought that wouldn't work. I don't know. Something about this is kind of interesting. No, because the no, but if you negate this, what if you just did this? I don't know. Okay. Okay. Sure. I don't know. It's still negative. It's not. No, there's got to be a way to take this number and basically bit shift it. Pretty much you're going to take n and you're going to say every other value of n, we're going to flip that to a 1. But the problem is that there are values beyond n that are zeros, those would get flipped. If we use this integer, we get flipped to a 1, which we don't want. Every other value of n below the most significant bit, we want to flip to a 1. That's pretty much what we're doing. But how do we do that? You need the most significant bit of n to do that. So it would seem. Let's ponder that for a minute or two here. It's kind of what we're doing. Huh. There's gotta be another way to do this. It's like clever bit manipulation shenanigans. It's gotta be a way. Yeah, every other bit from right to left, starting with the first bit on the right. We'll flip those bits to true on n. However, well, let's first like analyze that hypothesis, right? Yeah, let's do this. Okay, what does that do? Wrong answer. Really? X is 1, or equals x. X is less than n. as soon as it's larger than n. Oh, excuse me. Bit shift that by 2, not 1. Wrong answer still. You're kidding. What? Come on, what? No. I feel like I'm so close here. Feels like I'm so close. So if we had 9, I want to get 6, right? What? 9 is 1, 0, 1, 0, dot, 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 dot. Excuse me. And to get this 6, we're going to say we or equal 1, 0, bit shift 1, 2, and then this is 1, 2, 4. By the way, this is wrong. Zero, 1, 0, excuse me. 0, 8. So I said you're always going to have all of these, which is also wrong. I don't know why did I think that? Wait, what? Toggle is true. If toggle, then add step, which is 1 initially. Then toggle is false. You don't add 2, which is now 2. You may or may not add 2. And then toggle is true again. And you would add 4. Now how does this work for... Oh, because you start off at 1. That's why. Oh, interesting. So actually, it's a little bit different than that. Adding to 1. Not the same thing as flipping those bits. So I'm actually wrong. Okay. Got it. Okay. You're actually adding that you're not adding 1 to that, but you're adding all of this stuff, this whole number, you're adding it to 1, which is almost correct. It's almost what we had. It's not that n. So the thing is, shouldn't this just be 5? That should be n plus 1 here. Why did this get all the way to 8? What happened? This is the number that we add. So we have 1, 0, 1. Now, the thing is, right, t's got to be greater than 1. T is the number of elements, by the way. So that's why we don't go all the way to n, because it's more like n divided by 1. Hold on. Yeah, I don't know. It's more like this. The algorithm that we want is more like this. Still wrong. Nice. Yeah, okay. Oh boy. Okay, so I guess forget all this other stuff I was trying to do with the bit manipulation. And I said briefly revisited, it's already been half an hour. What did I do, man? What did I do? Whoa. Whoa. Okay. Interesting. Interesting. Yeah. Wow. Wow. Right. Okay. I don't know, man. Oh, well, you're supposed to include the n, the parts of n that are there too. I think it's XOR with n or with n. I think that's a part I missed. Still wrong. I'll put 14. Gotta subtract the most significant bit, I think. Yeah. Feels like you need to know the most significant bit of n for this to work properly. How do you get rid of the most significant bit? How do you do that? What if you flipped all the bits and then bit shifted to the right? Or you n without the most significant bit, call that t. If you take n, flip all those bits, right? Then and it with n again, what happens? Should just be all zeros. That's just all zeros, but fair enough. True. Absolutely true. Like I know this one. This'll remove the. This does something interesting. What if you did this? Well, I don't know. What is? This I think removes the least significant bit, but we want to remove the most significant bit. What if we did like both of these negated and then negate at the end? Like, what does that do? What if you? I don't know. I don't know, man. Let's just say. How do we remove the most significant bit? How do we do that? That's basically what we need to do. It's pretty much the problem here. 1 0 1 0 1, right? Let's try that. Okay, we want to get rid of this guy. There's a bunch of zeros over here. Well, if we flip all these bits, we still have this part, right? So whatever we get, we really just want to get rid of this spot because we don't really care what's over here ultimately, because this we can just kind of oh no, we do care what's over there because We can't just OR with this guy because we're trying to get rid of this guy. We're actually trying to get what's over here. That's the point. That's actually exactly what we want. Can we get a bit mask that's just all of these guys? Can we do that? How about that? What happens if we do that? If we OR with all ones? No. Can't XOR with all ones. XOR would, of all ones, would make all ones on this side. It basically would just bit flip everything. Which is fine, I guess. How do I get this mask? How do we do that? From here to here. Do some bit manipulation to make that happen. So the thing is, we could just remove all the bits or something. That's not really what we want to do. I'm trying to actually avoid that. What if we shifted all these bits? I mean, that's an idea. Bit shifted would look like this. Huh. Interesting. Negated. And then take the XOR. Oh, that's pretty good. That's actually almost what we want. And then negate again. And then bit shift to the right. Oh no, that's what we want. What did we do? Bit shift to the right. Negate. And then what do we do to get to here? Do we say we XOR? No, XOR gives us the whole thing. We want wait, what did we do? How did what? What did I do? What did I just do here? Wait, what? What? We didn't AND these because this will just all be. These are all be zeros. I'm so confused. Oh, I think I did an XOR with the original. Oh yeah, okay. N XOR X, let's just call it. Or T or whatever you want to, yeah, I don't know. Previous. Oh yeah, if you XOR this guy with this guy, this bit should be a 1, that'll be disappear, but all these other bits should be flipped, I guess. Yeah, because this is negated. So all of these bits will be 1s moved over, they become 0s. So when you XOR them, all of the 1s have a 0. So the 0 and the 1 will give you a 1. And then all of the 0s become a 1. Right, so the XOR should, oh yeah, that works. That's interesting. And then you negate this one more time. Wow. There you go. And then, oh, cool. And now you can just bit shift this one more time to the right and AND it with original N. And there you go. Whoa. Huh. Whoa. Okay. Let's try that. I like that. This is some fancy footwork with our bit manipulation. I don't even know what I just did, but I like it. So, okay, int t is going to be n, bit shift to the right 1, negated, then XORed with n, and negated one more time. This is going to be the mask. And then that whole thing, I believe we bit shift that one more time. So this will give us all of n that we want. We bit shift that to the right one more time. And that'll basically, we can AND that with n to get rid of the most significant bit. And then we bit shift that to the one more time to the right. And we're going to say, back to what we were doing before, n XOR that and the mask. Something like this is what we're looking for. Okay, totally wrong. Got 4, expected 6. Okay, what happened? What? Okay. What is going on? These are all random numbers, but we'll just save them for the sake of it. What happened? Oh, the mask is 6. Interesting. Huh. What? N is 9. That's good. Nine looks like this. 8, 4, 2, 1. And what we said was the mask is 6, which is 1, 0. No. What? That's not right. The mask should be 6. The mask should be 7. Why is that? What? Okay, if you bit shift to the right 1, 0, 1, 0, 0. Just call step 1. Step 2 is negate this whole thing. 1, 0, 1, 1. Step 3 is XOR this with n, the original. Which gives us 0 here, and this, oh, that's a 0 there too. Uh-oh. That was supposed to happen. What? Excuse me? Also a 0, 1, 0. Oh. Okay. And then what? Very confused. Yeah, very confused. I guess this doesn't do what I think it does. Bit shift 1, so you have zeros, 0, 1, 0, 0. Negate that, so 1s, 0, 1, 1. XOR with this guy, which is a whole bunch of zeros. So we get a bunch of ones, except at that one spot we get a 0, but this is also a 0. That's kind of a concern, isn't it? And this 1 and 0 is a 1, and this 1 and 1 is a 0. And then you bit flip that. Why did I think this was going to work? That's not what I was expecting. Oh, I think I was supposed to... I don't think this is supposed to be N. I think this is supposed to be N bit shift to the right, 1 XORed. I mean, I'm really confused, but I don't know. I don't know what I was supposed to do here. How did I get this? How did this happen? Was this just random? Maybe this is just by chance that this happened to do what I was hoping for. Oh man, this is taking a lot more than a few minutes. I thought it was going to be like 5 minutes to do this. Bit shift to the right 1. Flip all those bits. And then take a... Wait, this should have been a 1 here if this is an XOR. Wait, what happened? Hold on, what? Well, this XOR 0 here, 0 there, 0 there, 0 there, 0 there. Yeah, it's the original N. No, yeah, it's the original N that you XOR with. Well, what if the original N is just like a bunch of random stuff, or just a bunch of ones? I don't think this is right. Let's just try like a bunch of ones. Let's try that. Bit shift to the right. Take the XOR, or negate. Bit shift to the right, negate, and then what do we want to do? I mean, this already has a mask, but that's not really the important part. We're trying to generate the mask in all cases. Bit shift to the right, and then negate. What's kind of interesting is what if you man, it's very challenging. This is tough, man. I don't know if I could do this the way that I want to. I think you have to do it in a way that's like not. Oh man, shoot. 1, 2, 3, 4, 5. No, that's not a good example. I think 9 is like the best example. That's kind of an awkward kind of a position to be in. So our goal, if we flip these bits, looks like this. And if we were to XOR them with the original, we're definitely going to have that first, that most significant bit will be gone. But we're also going to have some garbage here. Right, this is what we want, but this is going to be uncertain. Now this part we basically want to be the same as this. It's kind of what we're trying to do. We're trying to get a mask that's just all of these bits. I mean, you could build this mask in a mechanical way, but like that kind of defeats the purpose of the thing we're trying to do. We're trying to do this using just like bit manipulation. Basically want to convert this into this. How does one do that? If you could swap all the bits, flip all the bits, swap all the bits, you could do this kind of easily. Not swap all the bits, but like reverse. If you could reverse the integer, that would be easier. I don't know how you reverse an integer though. Reverse the bits in an integer. Then this is very simple to do. This is a simple thing. I wonder what the reversed integer would be. Wondering if there is like a simple calculation you can do to get the reversed integer. I don't think it's a simple way. I don't know. Reversing integers seems, yeah, I don't know about that. Let's not try to pursue that. There might be a simple way to do it, but I don't know of it. I don't know it. How do we go from there to there? Can we go backwards? Maybe from here to there? Yeah, I mean you could bit shift to the left one and then OR with 1, right, to make sure these bits are all set. And then you can AND this. That's a mask, and you can AND it with this. And you'll get the original again. Sure, but that's kind of the point, is we want a mask to be able to do that with. Maybe. Oh, what if we take a full bit set and AND it here. Well, oh, we can. No, I was gonna say we can AND, we can XOR, but that doesn't really help. Like no operation with the full bit mask really helps us, because it's just going to it's going to operate on all the bits, right? Like it won't really differentiate between this part of the bits and that part. That's not really what's going to happen. Okay, I know we can bit shift this to the right. I mean, like that has some value. That does something. 1, 2, 3, 4, 5. 1, 2, 3. Yeah. Question is, like, what meaning does that really have? What value does that really have? You can flip those bits. You can and that with the original. I don't think that'll matter. You can. I know you would. I know if you were to AND this with the original, you would at least remove the most significant bit, but you'd still have 2, 3, 4, 5. I think it would actually be all zeros at that point. That doesn't really help you, does it? It's like, well, great. What do we do from there? I don't know. I don't know, man. I don't see a way around this without doing like a bunch of operations manually. It's kind of disappointing because I thought it was so clever, you know, reducing the algorithm to something a little simpler. But I don't think there's an easy way to do this. Yeah, I've looked at this question before, and I've kind of run into the same problem where finding the most significant bit is kind of challenging. Yeah, I mean, shoot. Excuse me. Need to go to bed too. Maybe I'll just leave it. It's really interesting question here. Just thinking, yeah, all that doesn't make much sense. Excuse me. Yeah, current is 1. Add these steps. Always add the first one. Add 1. I mean, you basically could start off at 1, 0. It's always going to be at least 2 from what I can see here. Sort of. Not quite, I mean, if it's a 1. Okay. Interesting. Excuse me. I mean, I like what it did here. It's like very clear what's happening, but can you do? Wait, can we change this slightly? Hold on. What if we did this? We don't really need a toggle, do we? What does this do? Wrong. Nice. If toggle is true initially, then just thinking here. This should start off at 1. toggle is true initially, then step really starts off at 2. A little confused, but no. What? Hold on, hold on. Okay. So we take this and we say I don't know. Oh yeah, fine. And we say we're not going to use the toggle anymore. So, well, toggle is true initially. We add step the first time. Oh, we're going to actually do both of these then. We're going to skip both of these. We'll do step in 2 pieces. Skip toggle. Add current the first time. Right. And now that means the step see, that is confusing. I don't know what's going to happen here. Kind of guessing what these numbers are supposed to be now. Nice. Yeah, make it 2 hops now instead of 1. Skip the first one, I think. Yes, you skip the first one because you're already going to add that. You only care about this one and every other one. And I think for that reason you also current starts off at 2. The step I think starts off at 3 then. No. Step I think also starts off at 2. Or yeah, 2 or 4, I don't know. I want to say it's 4. That's so confusing. Basically skipping the first toggle. The first iteration. I don't know how I wrote this so succinctly. Like, this was done really a lot better than probably could have done it. Anyway, so kind of funny, but we skipped the first step. Say we skip the first toggle. That means we're going to skip this guy, right? First iteration. And we're also going to we skip the first iteration, which means toggle is going to be false. Current's going to have that first step, which is 1. It's going to be appended. And step is going to be 2. Right? Okay, still the right answer. Not for all inputs though, right? If input is 1. Yeah, now we have sort of a base case. I was gonna say, I don't think we handle that case. Okay. But now the question is, we don't need to do, toggle is initially false. We don't need to do this next case. So we could jump right over it. here's the question. Yeah, since toggle is false, we don't care about it. And in fact, toggle is going to be true. Oh. But we're trying to add all this stuff in between, not skip it. Oh. That's why. Oh man. Such a confusing algorithm. Yeah. I don't know, man. I don't even know how it. What do you even do? I don't know. It's too funny. No, I don't, dude. I don't know how I would have expressed this without doing it exactly the way that I did. It's just exactly the way I did it. It's like so clean. Just gets everything. It's pretty funny. It's just nails it. Maybe I'm just wrong, man. Maybe this is just it. It's the only way. It's the only way. It is 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 the only way. This is kind of like, I don't know, it's like if we had to unroll this loop, right? Plus equals step, which is 1. Toggle is true. If tn1 or t bishop to the left and 1 plus equals 1 bit shift to the right 1 time. And then this is pretty much what we're doing here. Current 1 bit shift to the right 2. This is now 1, 2, 3, and this is 3, and this is 4, 5, 5, 6, 7, 7, dot, dot, dot. It's pretty much what our algorithm looks like. Yeah. Huh. Like all of these things are just t, right? Like everywhere that t has a 1 or a 0 here, like this is literally just t. The only thing we're really doing is that every other bit we're flipping to a 1 on t, all the way up to the maximum, all the way up to the largest bit. That's what I was trying to do. Mind you, now what's interesting about that is that's if current was 0, then we have to add 1 at the end, because apparently current starts at 1. But that's still the same thing. If you said, make this some other number, these are all the additions that we're making. So we just add 1 to the very end, and we're done. The problem here though is we don't know what the largest bit is. So it's challenging to flip all the odd indexed bits, or the even, or yeah, the every other bit from right to left, flipping those on to those on is just say it's challenging. All right, let's try that. Let's try a different algorithm. Let's give it a shot. Let's just like check to see if this is the right idea, at least. Okay, here we go. We're actually going to go ahead and build this thing. While, so for okay. Okay. So this isn't quite, so we add 1, we add 4. See, that's not really right either. This isn't really correct. This is so confusing. Add 1, then step becomes false, step goes to 2, false, step goes to 4. 1 goes to 4, we add 4. So we have 1, we have 4. Yeah, no, we're fine. This is okay. This is what t is supposed to be. And then return n or t plus 1. Is that right? Am I crazy? No, that's wrong. Oh. There's an extra 8 in there. Yeah, I think it's supposed to be. I think we were looking at this before. We were trying to figure this out. Oh. What? What? What do we get for t? 1? Oh no, we were right. Oh, I think I remember now. Right, we didn't. No, the problem with this is we don't want the most significant bit of n. The most significant bit of n actually gets thrown out at the end. Believe it or not. That's why this t greater than 0 is significant. Wow. Wow. Okay. No kidding. Dude, how did I do this? I feel like such a genius now, because every time I try to manipulate this, it just comes out wrong. It doesn't work. You gotta be kidding me. Must be some kind of genius. 5, 14, 6. 9, 5, 14, 6. No, 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 it doesn't work. It does not work. Yeah. Well, in that case, yeah, that's probably ran into before. So I think we just do a while loop, right? So what you do is you do x minus 1. In order to move the least significant bit, you do x minus 1. And then you AND that with x. And that should remove the least significant bit. And you do that until x is a power of 2. And to check out the power of 2, you say AND minus 1 equals 0. So the way this works is x and x minus 1, if that is 0, then x is a power of 2. X is a power of 2. Well, it's not a power of 2. We're going to keep doing that over and over again. And now we have the most significant power of 2 of most significant bit of x, or of n. And then we can say let int t equal n minus x, or XOR. Doesn't really matter. Now, now we can do these other operations here. First things first, could use a mask. It's just x minus 1. And then what we can do with our mask is n or this guy. I think it's this one. And the mask. I think that works now. I'm afraid it's not going to work. Time limit exceeded. Nice. Can actually just do this. Oh, that's interesting. That's really close. Oh, I think it's a +1 at the end, by the way. I think that was what we kind of determined before. I don't think this is much better than what we were doing before, quite frankly. Alright, let's go for it. Nice. Not better than what we did before. Not better at all. In fact, probably worse. Or equivalent. How are we going to figure it? Awesome. Spent almost an hour and 20 minutes. No improvement. Little to no improvement. Okay. That's funny. Trying to somehow use less memory. Not really getting there. Briefly revisited, right, briefly. Okay. I like this better. This is simpler. It's clean, it's easy to understand. This is a mess. This is like, what did you do? Why would you do this? You can take out the mask. It's definitely not better. Does it really matter after all? No, it really doesn't. It really doesn't matter. I mean, okay, I guess. I don't know. Could remove X maybe. Just make it N. No, you need the original N to put it here. Yeah. Huh. Right. Okay. Yeah. I don't know, man, what to say. All for naught, right? How about this? I think this is just better. I like what I did here. Because this is so much easier to understand. I mean, I guess you could explain this here. But I mean, if you're already doing something like this, then you might as well just do this. I think it's fine. Pretty interesting. All right, I'm gonna go. Oh, good enough. Good enough. 92%, 100%. I'll take it. All right. I'll move on. All right. So it looks like I wasn't able to get some fancy bit manipulation stuff going. I thought I could, but this is kind of fancy. Not too fancy. Just retrieving the most significant bit and then using that to build a mask and then masking off the OR of this. Yeah, I think you're kind of stuck doing the logarithmic portion of the algorithm to get the most significant bit. I don't know. I couldn't think of another way to do this. Couldn't come up with a better way. Maybe there's a way to do this if you like negate things, possibly. I'm tempted to look at the discussion to find someone doing it in constant time. We should do that. Yeah, we should do that. Recursion, whoa. Huh, really? Nobody got it constant time, huh? I guess you really can't then, huh? Yeah. Alright, fair enough. Okay, well in that case, I'll move on to the next thing here. So yeah, thank you for watching. I will talk to you soon. Have a good rest of your night. This was a challenge, man. This is a challenge. Alright, take care. Talk to you soon.